Okay, good afternoon. Um, Actually, today morning, shit happened. I have forgotten to press recording, so I failed to record the lecture. And I'm going to record it now, repeating the lecture for myself, basically. Okay, so I'm sharing the screen. Sharing the screen now. Okay, I hope you see the slides. Yes. Swap parameter. Okay. Well, so we discussed today the kinematics of random walks. This is the third lecture about random walks. On the first lecture, we discussed that basically that it's possible to introduce infinitely many different random walks on a graph or relational database. On the second lecture, we learned that all these random walks basically corresponds to a particular resolution, okay, with respect to, with which we are going to apprehend information, right? So on the second lecture, we learned that each transition operator involves particular information content, and some information might be predicted, some information are just, some information is just noise, okay? So it does not follow from the previous history, nor has any repercussions for the future, okay? And in principle, knowing the graph, knowing the structure of the database, you always can estimate the amount of information which can be predicted and the amount of information which cannot be predicted by any means. Okay, so it might be that some particular resolutions of the data are non-informative and vice versa. Some resolutions of the data might be very important. Okay, now the last lecture, I'm going to explain what could we learn from if we define about the graph or a database, if we define random walk. Okay, so we don't measure the amount of information. We now learn how to extract this information. Well, also my talk has a second subtitle, Introduction to Machine Learning, because that is what's going on. What is a machine learning? The major concept is that data itself, which presumably exists in some real space, might have, and probably this real space is low dimensional, like a graph, two-dimensional, or, well, but in the data we don't have Euclidean distance. Moreover, we usually don't have any geometry. We don't have distances, we don't have angles. We are not able to understand whether some two or three entities are close to each other, or we are not able to cluster data patches together if they are similar, okay? But in order to do that, we construct what people call feature space instead of usual coordinates, so to say, or entities which we work with. We think about a feature space, some hypothetic geometric space in which all points and objects can lay, right? We embed them into a feature space. The most important property of the feature space is that there might be geometry, there might be Euclidean distance, there might be notions of distances and angles between data patches. And then we can use, once we embed what we study into a feature space, and in the feature space there are distances, and we can say that these two guys are close to each other, so I put them in the same mold, and that guy is very different from both, so I should lay them apart. Apparently it belongs to some other cluster. Okay, so this procedure is done automatically, and that is called machine learning. So machine learning is, roughly speaking, embedding into a feature, presumably high dimensional feature space. That's what I wanted to say. Okay, so I'm going to demonstrate while discussing the random walks. We would construct implicitly the machine learning procedure. Okay, so first, random walk on undirected connected graph. So once you remember that once we have an adjacency matrix of undirected connected graph, we may construct a row stochastic matrix. Row stochastic means that if I sum all elements in a row, I have, well, they should sum to 1. Okay, so then I have a row stochastic matrix. The left, okay, so I just take a laser pointer. Left eigenvector of the row stochastic matrix corresponding to the maximum eigenvalue 1 is a stationary distribution of random walk. Please note that if I take the right eigenvector of the transition matrix, it is also it is right. It's just a vector of ones, and it is right eigenvector of the transition matrix. Stationary distribution of random walk is given by left eigenvector of the transition matrix. Second step, I symmetrize the transition matrix by performing a similarity transformation with respect to a diagonal matrix of elements of the stationary distribution, major left eigenvector of the transition matrix. Okay, so I construct the diagonal matrix, and I multiply my transition matrix from the left by the square root of pi, and from the right by negative square root of pi. By doing that, I construct a symmetric matrix. This is a similarity transformation. Therefore, eigenvalues should be the same. Eigenvectors are changed, indeed rescaled, but okay, so we diagonalize this. We diagonalize the new symmetric matrix T, and then we have a set or a matrix of orthonormal eigenvectors psi and diagonal matrix of eigenvalues mu. Okay. Why the matrix is orthonormal? Because the initial matrix T hat was symmetric. Look, that T transition matrix was not in general symmetric, but we symmetrized it, and therefore the resulting eigen decomposition is constructed with orthonormal vectors. These orthonormal vectors plays the role of features, and the whole vectors of the matrix psi, the columns of the matrix psi, give us they span the whole feature space. This is random walks is the unique situation when we can construct our feature space explicitly, right? Okay, so just really, because in most of other cases, especially for neural networks, nobody knows how this feature space look like. Okay. If I look at the eigenvalues elements of the diagonal matrix M, I can order them. All of them are real, so I can order them. The biggest one is mu1 equals 1, as usual for random walks. The lowest one is a little bit higher than -1. Okay. So what is the meaning of these eigenvalues? If I take a Poisson continuation of jumps, switching from discrete time random walks to a continuous time random walk, then I would get for every mu k, for every eigenvalue of the transition matrix, an expression that there should be a process proportional to exponent negative t 1 minus mu k. And therefore, 1 minus mu k, 1 over 1 minus mu k, is nothing else but the relaxation time, the time when the particular process of transition to a stationary distribution decays, extincts, or ends, fades out completely. Okay, so it's some characteristic time scale. So when we diagonalize the transition, normalized transition matrix, we see that we have a set of time scales. Mu1, the biggest eigenvalue, if I plug mu1 here in this formula, I have 1 divided by 0. That means infinity. So this is an infinite time scale, infinite relaxation time. This is a stationary distribution of random walk. In order to prove numerically the stationarity of this distribution, I, formally speaking, should observe these random walks for an infinite time. Now, psi, eigenvectors psi, all of them are orthonormal. That means that if I, if I just sum squared elements of these of any of these eigenvectors, I get 1. That means that all of them belong, all of them lay on the surface of a unit sphere in n minus of dimension n minus 1. Okay, so these are orthonormal vectors. All of them lay on the surface on a unit sphere, and mu eigenvectors defines the relaxation times. Well, so that is what we have, what that setting we have. Okay. Indeed, we can assign probabilistic meaning to every object we have mentioned. All algebraic objects could have some meaning, probabilistic meaning, if we think in terms of random walks. First of all, squared elements of the major eigenvector, the first Ferron-Frobenius eigenvector of the symmetrized transition operator corresponding to the eigenvalue 1, the squared elements are nothing else but pi. You remember that if I take the row stochastic matrix itself, the left eigenvalues are eigenvector elements of the left eigenvector is pi. Okay. Here I perform the similarity transformation, and now in my similar symmetrized matrix, a stationary distribution is the squared elements of the eigenvector psi. I like to draw your attention to the fact that we actually works in a setting very similar to quantum mechanics. Once upon a time, Heisenberg invented wave functions, basically. Okay, so he considered the self-adjoint elliptic operator, which he called Hamiltonian. And the setting was pretty well the same, and the meaning of the solutions of this Schrödinger equation was that squared elements of the solutions have the meaning of probabilities. So psi here are nothing else but wave functions of the graph, or random walkers on the graph. So if I consider the element 1 minus pi I, it's always positive. It should be equal to sums of squared elements over all other nodes S. S starts from 2 to n. And this quantity can be interpreted as the probability that a random walker is not in I. So remember that sigma squared 1i means that a stationary distribution of random walks is a probability that I can observe a random walker in I. And here I have the probability that a random walker is not in I. Now, each element squared squared component of eigenvector S, ith component of the eigenvector S, is the probability that a random walk detected at I contributes to the relaxation process, S relaxation process. So relaxation process characterized by what? By the relaxation time 1 over 1 minus mu k, mu S in our case, right? What else? Now, signature of a graph. So let us consider a little bit the matrix of orthonormal eigenvectors of the symmetrized matrix T. So first of all rows of these matrix, if I calculate a scalar product of these vectors, I have a delta function. If I and j coincide, the vectors are the same, I have 1. This is orthogonality. I mean, this is a normalization condition, right? If they are different, I and j do not coincide, then I have 0. So they are orthonormal to each other. Scalar product equals 0 if I and j are not the same. Now, if the matrix of such kind is called such type, where all columns are orthonormal, are called orthogonant. So determinant of this orthogonant equals either +1 or -1. It is called sometimes signature of the graph. Well, if we have +1, it means that all transformations prescribed by these vectors are rotations. If it equals -1, it means that it also contains reflections, odd number of reflections, improper rotation, rotoreflection. Okay, now any part basically of orthogonal matrix is called minor. Okay, I will denote minor in this way. I select some elements I1, I2, Ik, the minor order of order k, right? And also some modes S1, S2, Sk. So my rectangular table here of elements is called a minor. Next step. Interesting property, fine property of an orthogonal matrix. Okay, so well, yeah, it just next step. But before let's just, I should also say that what is a cofactor? For every element of an orthogonal matrix, not necessarily a single one, but maybe a minor, I can find a cofactor. For instance, if I have a single element, I should take out the row. I should take away the corresponding column and then collect all remaining parts of my orthogonal matrix and calculate its determinant. I should also remember that I should add -1 in power of I plus j is the number of the order of transposition in my expression. This expression is called cofactor. You probably know how to calculate the inverse of a matrix, right? So this we should calculate a cofactor for every element of a matrix. That's why how we calculate the inverse. For an orthogonal matrix, there is an interesting property that the value of every element numerically equal up to the signature of a graph, numerically equal to minor to the cofactor. Okay, take a minor, take its determinant, and take into account -1 in a certain power. Okay, and then you find precisely the element you have missed. Okay, so I extracted this row and column for this element, and the value of this element always equal to the remaining minor, to the cofactor of this element in the orthogonal matrix. Example, I can take the element of the first major Perron-Frobenius eigenvector psi, but also I can take its cofactor, determinant of this minor, and the results are the same. For orthogonal matrix, this is even true if I consider not a single elements, but some other higher order minors. This minor would be numerically equal to its own cofactor, this minor. So, in fact, it appears that I can construct not only the frame of reference, including every node of the graph or a data patch, but also all combinatorially many different frame of references for all possible correlation functions that might be defined over this data. So what means a correlation function? It means that I can choose particular nodes, and I can choose particular time scales during which these nodes are observed. And then I can calculate its determinant, and this is numerically equal to its cofactor. Interestingly, that all these minors satisfy the same orthonormality conditions as we had for a single orthonormal vector, okay, in the system of orthonormal vectors. So before, I consider a scalar product of orthonormal vectors, and I have either 0 or 1. Now I can construct the combinatorially many combinations of minors of particular order, and all of them have the same orthonormality properties. So the orthogonal determines a set of basis vector, because you see that there might be very many combinations, very many minors I could construct of particular order. I could construct from the elements of this orthogonal matrix. So I have a multidimensional space spanning the space of all possible correlations functions also. Well, interestingly, that all these quantities are properly normalized. If I want to know what is the probability to observe a random walker in some sequence of node or some group of nodes for each node, I should provide particular time scale or characteristic time during which I'm going to monitor what's going on in this node. And when I constructed this minor, I can calculate its determinant, its squared matrix. I calculate its determinant. I squared this determinant, and then I have some number in between 0 and 1. And this number gives me precisely the probability to observe a random walker in the particular set of nodes during particular time scales. Okay, the story is just the same as we had for a single nodes. We worked with a stationary distribution here, right? But if I am not interested well, station distribution means that I have a node, take a node, and observe its history for infinite time. Okay, here I have a subset of nodes and observe them not in infinite time, but with some sequence of time scales. Take the determinant, calculate the square this determinant, and then this is your probability. Example, okay, stationary distribution of random walk. I take the minor of order 1, anchored at node I. Indeed, it equals its determinant itself, and I squared this element. As a result, I have the stationary distribution of random walks. This story, what I explained you about orthogonals, had been published by British professor James Muir. Before, the last time it was published in 1914, just before the First World War. Since then, these results had been completely forgotten by mathematicians. Now, certainly after this, during the wars, a lot of 2 wars in a row, many people had been just killed or died, so they did not inherit this knowledge, so to say. Interesting story. The last use of these methods had been reported by Slater. Slater was a physicist. He worked in quantum mechanics, and he noticed that determinants have the property of quantum systems, in a sense that if we exchange the coordinates of some object wave function, then this wave function should alternate its sign, and determinant is very similar. If I exchange the orders of my rows or columns, then the determinant must change its sign. Moreover, all rows of a determinant, also if it's a quantum mechanical system, it should be orthogonal to each other. It's a Pauli principle. So fermions, electrons with non-integer spin momentum, should occupy separate, different, distinct levels of energy levels. Okay, so here the system was this determinant of orthonormal vectors behave itself precisely like a system of wave functions describing atoms with many electrons. Okay, so this is what people call Slater determinant. It's a model for quantum mechanical description of multi-electron atoms. The squared of this matrix, of these determinants, equals the probability to observe electron 1 in energy, having energy x1, electron 2 having energy x2, and so on till xn. Okay, so this is the use of orthogonal matrices. It was proposed in 1927, so 13 years after publication of the book, of the Muir's book. And that's all. In mathematics, we don't use anymore the properties of orthogonal matrix. So that's the first story. The summary of the first story is that we can indeed calculate, we can define an orthogonal system of coordinates, frame of reference, Cartesian coordinates, on any database or a graph. Moreover, we can construct a Cartesian orthonormal orthonormal frame of reference, not only for particular data patches, but all groups with respect to some time intervals, time durations. Second part of my talk. Now, let us learn. So we define the frame of reference. Now we should define distances and angles. Okay? So it's a real geometry. We geometrize data. We geometrize graphs. Okay? We introduce the frame of reference. Now let us learn how it's possible to measure distances. Measurements of measuring distances. Well, people use access times, or sometimes they call it hitting times, first hitting times in between I and J, two nodes in a graph. I start in I. What is the expected number of steps required for me, if I'm a random walker, required for me to reach J for the first time without loops? You may say, it has no big meaning to measure distances by random walks. Indeed, I can got stuck in some I can just get stuck in some intermediate node and performing loops one by one infinitely many times and would never reach J. But if I have a random walk, then every trajectory could be characterized by a particular probabilities to be observed in the walk. And if I perform many loops, such random walk has very low probability. Yes, I could travel from I to J infinitely long time, but such a very long trip would have probability close to zero, because every loop reduces the probability by 2 or by factor number of neighbors within at the node. Okay, so it's really possible to calculate a finite expectation values for distances and for distances between nodes. Okay, so people consider a matrix H, I, J. So the access time, how many steps is required to go from I to J. This matrix obviously should satisfy the following matrix equation. I suppose I made a single step from I to L. L is a neighbor of I. And then I should go from L to J. So this is a one element H, L, J now, okay? What is the probability that I go to L? This is a probability of transition from I to L, and I've made a single step, so this should be here should be 1. So this is a definition of a concept of access time. Indeed, if I just try to solve this equation for H, I, J, I would see that this problem is not well defined. I have infinitely many solutions for this equation for all elements of these matrices. So I need to specify some initial condition. And my initial condition is such that I'm only interested in such trajectories, such access times, which would give me 0 if I don't go anywhere. If I stay at the node I and measure an access time to node I itself, where I'm presently located, then this quantity should be 0. Using this initial condition, this equation could be resolved, and this solution has the following spectral representation in terms of psi eigenvectors, elements of eigenvectors of the normalized, symmetrized transition operator, and eigenvalues mu, S2, S3, S4, and so on. Please pay attention that in this sum, we start indexing our terms from s equals 2. There is no term s equals 1 because mu1, the biggest eigenvalue of the symmetrized transition operator, is 1. Okay, so if I plug it here, I get 1 divided by 0. So this term does not exist. I start my summation from s equals 2. 2, 3, 4, and so on. Okay. Please pay attention to the fact that the quantity, or if you just look at this formula, you would see that, in fact, I have, well, it's very similar to some projection, okay? Projection is some multidimensional space, n-1 dimensional space. The first term in this sum describes me some squared norm of some vector. And if I think which vector is that, if I consider psi as weights and 1 minus 1 minus mu s, 1 over 1 minus mu s as a scaling factor, then I can see that I have a squared norm of a vector in n minus 1 dimensional feature space. And here, this term describes a scalar product between vector e, g, and ei, okay? So in fact, my vectors are basis vectors, right? Standard basis vectors on the graph. Zeros everywhere, excepting for some single position corresponding to the number of the node, okay? So that is how we constructed a feature space. The graph was a real space, and every node was characterized by a canonical basis, canonical vector in the canonical basis. And now, with these scaling, with these weights and scaling factors, we performed a mapping of these canonical vectors into some other high dimensional n-1 dimensional feature space. Okay, so that is the core of machine learning. Now, if this space allows for some distances and angles, we can consider these distance and angle quantities, which I show you, demonstrate you in the next slides, as a real geometry of objects in a real space. In real space, we do not have any geometry. We do not have distances. We do not have angles. In class, in the morning, I even use the structure of the class as an example of a graph. There are some corridors, some spaces between rows, but if I'm going to to meet a student sitting somewhere, I should somehow, I cannot jump through rows, okay? So graph, and every graph, actually, every structure, it's not Euclidean space, because first of all, I'm not able to go directly. There are some obstacles. Well, but nevertheless, I can map all this structure into a feature space. If I count the number of random walks required to go from one space to another space, I count these expectations. It appears that they follow, that the Pythagorean theorem still works. And that's what I'm going to show you. So, okay, so the quantity, the first heating time or access time, h, I can calculate the averages of these metrics with respect to the first and the second indices. For instance, if I take the average with respect to second index to where I go, actually, right? So I calculate, I make this simple calculation and get what people call the random target access time. If my target in the graph or in the data is random query, How long would it take to get there? It appears that the result is a sum starting from a second mode to n of 1 over 1 minus mu s. So it's a sum of all relaxation times required for random walks to completely will fade completely. I mean, the all time for transient processes to dies out, right? To dies out, to converge to a stationary distribution. If I take an average of the first hitting or first access times h, g with respect to the first index, I get a result which is known as first passage time. I know the node I, and I start from any particular, from randomly chosen node in a graph, or from random patch in the relational database, and follow some similarity, similarity weights. How many steps should I perform to reach I for the first time if I'm not going make any loops? In this case, the result is precisely the first term in the first hitting time. This is a squared norm squared norm of vector I in the feature space. Okay. Well, indeed, there are some relations between random target access time, first passage time. You could just I would skip this slide and just directly go to a commute time. What is a commute time? So commute time means, so I should start from I for the to j and calculate the number of steps required to reach j from I for the first time if I'm not allow any loops, any repetitions of symbols here. And then I go backward from j to I. Again, for the first time, I'm not allowing for any repetition of symbols here in my path. Commute time is a sum of hij and hji. Why I precisely specify this sum? Because that is what differs. That is how this random walk kinematics is different from the standard geometry we all used to. Because in a standard geometry, the distances, the space is isotropic, right? So if I measure a distance from I to j in real Euclidean space, and then measure the backward distance from j to I, they should be equal. Okay, this is not true for graphs and databases, because even in the regular graph, right? So these distances might be different. Structure creates anisotropy. Structure creates disparity between directions of movement. So I should take a sum of these two quantities. But if I take the sum of these two quantities and consider the spectral formula for them, I would see that it looks like simply a Euclidean norm. It's a Pythagorean theorem. So this commute time with respect to the first time and the first hitting time, it just restores the Pythagorean theorem over any graph or database. So that's what is actually important. Well, and basically I finished my lecture this morning on this cumulative, so to say, slide expressing the whole story. So I have a graph which is described by the adjacency matrix A. Adjacency matrix might be an affinity matrix or any relational database. I always, add this explanation. I can construct a diagonal matrix, sum of weights, okay, of my affinity matrix or degrees in case of if I think about adjacency matrix of the graph, I can calculate the row stochastic matrix, row stochastic transition matrix between nodes of the graph or entities of the database following similarity. Okay. Then next step, I perform a symmetrization of my transition matrix, which gives me the nice set of orthonormal eigenvectors and eigenvalues. Since this transformation is a similarity transformation, eigenvalues of original transition matrix, row stochastic transition matrix, are the same. The biggest eigenvalue is 1, and all others are less than 1. Okay. The squared elements of the first eigenvector are the stationary distribution of random walks. All other eigenvectors being normalized by the square by the elements of the first Perron-Frobenius eigenvector, which always is all elements are positive. Okay, there is no division by 0 in this expression. This is nothing else as a Gram matrix describing some scalar product of two vectors of the following type. These vectors are vectors of feature space. We start from nodes of the graph and there were no any geometry, but we switched to, had been lifted to a feature space. And in the feature space, we had a geometry, and this geometry is Euclidean. The dimensionality of this feature space is n-1, is n, if n is large, then the space dimension is huge. We lift whatever we had, graph or a database, to a high dimensional feature space in which we can define a scalar product, in which we can define the norm of a vector, in which we can define the Euclidean distance between vectors. These quantities could be interpreted as the first passage time to a node, commute time between nodes, and the Gram matrix itself is could be interpreted basically. We can measure the cosine of an angle between elements of the database, between nodes. In fact, if you have a look on the expressions in these elements of the vectors of a feature space, you would see that they look like stereographic projections from the direction psi1, direction with respect to which correspond to the maximum eigenvalue mu1 equals 1, and this term is absent in this sum, right? So it's a direction along which our operator would diverge. These projections, stereographic projections, constructing of an inverse using these stereographic projections is known as Dratzan generalized inverse. You know that there are different types of inverses of matrices which cannot be inverted directly. If a matrix has a zero eigenvalue of several zero eigenvalues, it cannot be inverted. And then there are different strategies how to invert such a matrix. First strategy is a Moore-Penrose generalized inverse. We simply get rid of zero eigenvectors corresponding to zero eigenvalues, and then recombine the matrix back. So we have a rank-reduced representation of the non-invertible matrix. It's called Moore-Penrose generalized inverse. And this is another approach. We take these directions along which the matrix is not invertible and construct a stereographic projection. And that is what we have for databases, okay? In fact, then, it's possible to show that the resulting manifold, data manifold, is now hyperbolic. It looks like these, knitting crochet manifold. Crochet in French means to knit, right? So it's a kind of the type of manifolds like that are called in mathematics hyperbolic spaces. So we really embed feature space are basically hyperbolic always. So we embed low dimensional features, lack of geometry into a multi-dimensional space with a hyperbolic geometry. The examples of applications of real world cases when we can apply these methods and what we could learn from them, I start my next lecture with all these examples. Thank you so much. I hope my lecture was useful. So what should I do? I should stop share screen. I should stop recording and see you next time. Bye.